In nature, confinement is crucial for the excellent performance of enzymes in a vast number of biological processes. In our CRC, we mimic these confined spaces using various mesoporous materials. We anchor tailored and well-defined organometallic catalysts selectively inside these mesopores, thereby creating a confinement for catalytic reactions that can outperform nature in terms of catalytic performance. To make this approach a success, it requires interdisciplinary efforts of researchers from material sciences, analytical chemistry, theory, organometallic chemistry, and catalysis.
As materials chemists in the CRC, our goal is to create materials with well-defined pore sizes, pore geometries, and surface chemistries in order to study the effects of confinement on catalysis. To make this happen, we use a broad spectrum of materials, organic, inorganic, and hybrid materials with pore sizes of a few nanometers. Example materials include silica or metal oxides, but also carbon-based materials such as mesoporous carbons or covalent organic frameworks.
Our catalysts use this special pore structure around them to influence factors such as catalytic activity, selectivity, longevity, or even specificity for certain substrates. In other words, to control which products we make and how fast they form. Using the principles that we've learned thus far, we can influence the reactivity of a diverse array of catalytic processes, including enantioselective catalysis, electro and photocatalysis, and even gas phase reactions.
So the outcomes of the A and B areas are immobilized catalysts inside the mesoporous materials and also the full catalytic investigation of these systems. However, to make real progress, we must understand exactly what happens under real-life catalytical conditions. To this end, we use a range of experimental techniques, some of which we develop ourselves inside the CRC to understand what the influence of immobilization on the catalyst is.
Quantum chemistry allows us to study catalytic reaction mechanisms, while coarse-grained molecular dynamics is used to simulate flow and diffusion around the catalyst inside the pores. The understanding gained by the combination of these methods allows us to improve the performance of our catalytic systems.
This joint effort in our CRC will ultimately help to understand catalysis on a more fundamental level. Furthermore, it will open up new possibilities to create so far unknown reactivities and selectivities in chemical reactions.